So I'm going to explain some ideas I've been exploring with Joy Leahy and Jeroen Jansen into addressing disconnected evidence networks. But before I do that, I might as well just motivate it and clarify what I'm talking about. So this work came from quite a little while ago in 2015, when I was trying to do a network meta-analysis in pulmonary arterial hypertension. And we wanted to compare, so don't worry about what the names of these treatments are, but we wanted to compare the combination E plus P5 plus PR to E plus P5 plus imatinib, and it's down here in the corner. And Dario, can people see my cursor when I move it?
Yes, we can.
Okay, so it's this bit down in the corner where we didn't have any randomized control trial evidence comparing E plus P5 plus PR to E plus P5 plus imatinib, and our network that was composed entirely of randomized control trials couldn't directly compare them via any of the other treatments. So what we actually did was we included some single-arm observational studies, for example, this Jacob study, which was comparing, or which had added E plus P5 plus PR to some patients, so sort of before and after study. But the only way we could include this in the network was to assume that the baseline effect, so the effect in our model of E plus P was randomly distributed across different trials, so that we could impute what would have happened on that treatment, and that was the only way we could connect our network. But obviously, if you're familiar with network meta-analysis, you'll know that this is quite a dangerous assumption and carries some potential bias into the rest of your analysis. So I'm now going to try to take a step back and explain why we wouldn't want to put a random effect on a baseline, and also clarify theoretically what the issue with disconnected networks is. So if you consider a very simple network where we've got 3 treatments, 1, 2, and 3, and we assume we've only got one trial comparing 1 and 3 and one trial comparing 1 and 2. In practice, it could be a meta-analysis of those. Then in randomized control trial 1, you've got 2 arms. In arm 1, you've got some response on treatment 1, which is represented as mu1. This might be the log odds of some event, like the log odds of relapse or the log odds of improvement on some disability score. And in arm 2, you've got the response on treatment 2, which is assumed to be the baseline effect mu1 plus the treatment effect of treatment 2 versus treatment 1, which is D12. In RCT2, you've also got an arm on treatment 1, but the response here is a mu2, so it's some other baseline effect. And on arm 2, which is on treatment 3, it's the baseline effect of treatment 1 plus the treatment effect of treatment 3 relative to treatment 1. So in standard network meta-analysis, we would cancel out the mu's because we assume that they're just nuisance parameters. And then we just subtract D12 from D13 to indirectly compare treatments 2 and 3. And in this case, the mu1 and mu2 are assumed to be completely independent, just nuisance parameters. And all the models that I'm talking about are fit through Bayesian, MCMC, and OpenBook software with vague priors, but I think you can do this in frequentist or Bayesian. It doesn't make a huge difference. Now, if we had a slightly more complicated network, we've got treatments 1, 2, 3, and 4, and we've now got another randomized control trial, this time comparing treatments 3 to 4, then the baseline effect, mu3, now corresponds to treatment 3. So this is just explaining that these mu's don't always have to correspond to the same treatment. It just has to be assumed to be the same in both arms because we're controlling for prognostic factors. So in arm 1, it's mu3, arm 2, it's mu3 plus D34. So we would again just cancel out the effect of the mu3s because we're assuming they're nuisance parameters, and we can get the treatment effect of treatment 3 versus 4. And then if we want to indirectly compare any of the other treatments in this network, we'll make the consistency assumption. So we would assume that D34 would be the same as the treatment effect of 4 versus 1 minus the effect of 3 versus 1. And we can rearrange this to give us the treatment effect of treatment 1 versus 4. So we've indirectly compared it using the evidence in our network. And similarly, sorry, the webinar controls keep moving around whenever I click something. Also, we could get that treatment effect of 2 versus 4 is just 1 versus 4 minus 1 versus 2. So if the network is connected, we can indirectly compare any treatment. Now, the model we're going to consider, just for simplicity, is binary outcomes. So we've got some probability P, IK on arm K of trial I. That's the probability of some event, say relapse or stroke, and that's out of a number of patients, NIK. And the probability of the event on arm K is just the logit of PIK, who's just mu I, so the baseline effect plus some relative treatment effect that's specific to that trial, that's delta I PK. And if it is the baseline arm, the logit of the probability is just the baseline effect. Now we can make assumptions about these relative treatment effects that are in each of the trials. We can assume they're fixed, so there's no randomness, or we can assume they're random, so they're distributed around the true treatment effects with some heterogeneity, standard deviation, sigma. If we're assuming baseline effects are random or are independent, then the mu i's are assumed to be independent across the randomized control trials. And this means that within the trial, the controls for prognostic variables, the prognostic variables are assumed to be balanced between the two arms, and they'll only affect the mu i's, not the deltas. So we cancel them out across the different trials. But if we assume that the mu i's weren't independent, so we put some sort of model on them, so say the mu i was normally distributed around some mean effect m, then it'll interfere with randomization, because the estimates of the D12 and the D13 might be biased. So this might happen because placebo response, if we're assuming that the mu I corresponds to placebo effect, could improve over time due to general improvements in therapy or expectations of patients. And this means that the random baseline effect would pull older placebo response up and push new placebo response down, and would therefore bias against older treatments. Now, however, recent work, or not so recent now, Bellevue 2017 did show that this bias could be limited in practice, where they did a simulation study in a connected network where they assumed the baseline effect was random or not. They found roughly the same results. So now that we've seen independent baselines in connected networks, we need to consider disconnected networks. So here we've got the same treatments, 1, 2, and 3, they're connected. And then also over here, a separate trial comparing treatment 4 to 5. So although consistency tells us the treatments 4 and 5, the relative vectors are D15 minus D14, we don't know what D15 or D14 are, as neither 4 nor 5 are actually connected to treatment 1. And similarly, if we had a single arm study on treatment 6, although in theory, we know that the response on that arm has to be some mu I dash plus a treatment effect of 6 versus 1, we don't know what that mu I dashed is. So that's why we can't connect this network or work out what any of the relative treatment effects of 4, 5, and 6 are compared to 1. So if we get this disconnected network, we might ask, why not just call it a day? Like, we can't indirectly compare them. There's no evidence, so we just say, well, we'll have to wait until some randomized control trial is conducted to compare 4, 5, 1, 2, and 3. But it might be that this is a rare disease, so running RCTs is practically impossible. So you're never going to get enough patients to compare these treatments. Also, treatments 1, 2, and 3 might be very old, so it may not be ethical to include them in an RCT, but we're still curious about how much better they are than the older treatments. Also, healthcare decision makers like NICE in the UK don't have the luxury of waiting. And if you don't compare 4 and 5 due to a lack of evidence, you're implicitly deciding that treatments 1, 2, and 3 are better. So there are various things that we can do. So if we did have individual patient data available for all the trials, then we could balance the populations between, say, trial comparing 1 and 3 and 4 and 5 in 3 different ways. So we could do propensity score matching or weighting, where we re-weight the patients or match the patients based on how close they are. We could do regression adjustment, where you just predict the outcomes in some common population, or you can put these two together and get doubly robust estimation. But these methods can only be implemented if we have individual patient data from all studies, or at least from 2 studies. but we rarely have IPD from all trials. So if you had individual patient data available for a subset of trials, for example, companies would usually have IPD from their own trial, but they wouldn't have IPD from the other trials. We could use IPD on treatment 1 to predict response of treatment 1 in the population of the 4 versus 5 RCT, or in that population of the single-arm study. And you can do this using propensity score reweighting, which is called matching adjusted indirect comparison, or through outcome regression, which is simulated treatment comparison. However, governments and academics will rarely have access to any IPD. So this is something companies can do, but usually academics can't do this because we don't have the individual patient data. So we could look for non-randomized comparative evidence. So, for example, we might have some observational study, like a cohort study or some registry that has compared treatment 3 and 4. So we have some relative effect, D3-4, but it's observational and potentially biased. We could make a simple approach and assume that this D3-4 is the same relative treatment effect that we would have observed in a randomized controlled trial, and thus end up with a connected network, which is mixing RCT and observational evidence together. Or if there was sufficient data available, say you had observational data and randomized control trial data on some of the comparisons, then we could try fitting a hierarchical model or some sort of regression model to adjust for the differences. But cohort and registry studies are not always available, especially for novel therapies, because it takes a long time for them to enter general practice and to be captured by these registries. Another thing you do is node merging or class effect models. So in this case, we've got this disconnected network, but we could just assume that treatments 3 and 4 are the same. And perhaps they're members of the same pharmacological class. Then there's some sort of justification for doing this, or they might be related in the class effect model, where we fit some sort of hierarchical model to allow them to vary but still be related. But this doesn't solve the problem of comparing treatments 3 and 4, as there's still no evidence comparing treatment 3 and 4. This would be a problem, say, for the DOACs in atrial fibrillation. And we might not be justified to assume that treatments 3 and 4 are the same, or indeed that 1 and 5 or 2 and 5 or any of these sort of combinations. So this isn't always a practical option. So if we don't have any individual patient data, we don't have observational comparative evidence, and we can't merge the treatments, what can you do? Well, we've explored 2 methods that use only aggregate RCT data to connect our disconnected networks. So the general problem is that we've got some disconnected study or single-arm study I-dashed, and in both cases, we're going to continue to assume the mu-i's, so the baseline effects are independent in the connected network. So we're going to preserve randomization in the network where we have randomized control trial evidence and not interfere with randomization. And in the disconnected bit, we're going to generate some mu-i dash for the single-arm study or the disconnected RCT using 2 different ways. One is reference prediction. We're trying to predict the mu-i in those populations. This is maybe a refined version of random effects on baseline. And second is aggregate level matching, where we try to find a similar study and assume the same response will be observed in the disconnected or single-arm study. And for simplicity, we're just assuming we're predicting treatment 1, but you could also predict treatments 2 and 3. So reference prediction, the idea is that on the connected component, as I said, we proceed with independent baselines, avoiding interference with randomization. But we do a meta-analysis of mu-i from the RCTs that have the reference treatment. So the mu-i will always represent response on the same treatment, and we keep this data separate from the independent baselines NMA, again, to avoid any sort of interference with randomization. We then fit a model with or without covariates to these mu-i's, and then take the posterior predictive distribution in the disconnected RCT or single-arm study to get this mu-i dash pred. And this is our prediction of what the reference treatment would have done in the disconnected study or disconnected RCT. Aggregate level matching, instead of meta-analyzing all of the available studies, we just choose the best matching RCT with any baseline treatment TIB. So it doesn't matter here if we're choosing treatments 1, 2, or 3. We can use a mixture when we're matching, we just choose the closest match. So we choose this match based on, say, Euclidean distance on baseline characteristics like age, gender, baseline severity, duration of disease. And then in the connected component, we fit a standard independent baselines model, but use the independent μi from the best matching RCT from this independent baselines model, and assume that that's what the response would have been in the disconnected portion of the network. We try to make it a bit less precise by modeling this this plug-in μi with being normally distributed around the observed μi, and then the sigma, which is the standard deviation of the estimated μi. And this gives us our prediction of the reference treatment in the disconnected portion. And randomization is again preserved because in the connected portion, we're just doing a standard independent baselines NMA. Just before I discuss the random effects on the treatment, are there any comments or questions or immediate concerns about what anything I've just said?
No comments coming through as yet. Questions?
Okay. So in all the results that I'm going to present, we have looked at both fixed and random treatment effects, but we did find that the fixed effects were giving far too precise estimates and not really accounting too much for the uncertainty that we would expect. So we found that fixed effects were giving very precise estimates with very poor coverage. So in general, we recommend random treatment effects, but to include randomizations to these two reference prediction and aggregate level matching models. So if we recall the random effect model, where the delta, so the study specific relative treatment effect, is normally distributed around some true treatment effect D with some heterogeneity standard deviation sigma. So for example, for a study comparing treatments 1 and 2, it's a delta I 1, 2 is normally distributed around D1, 2. And this heterogeneity variance, sigma squared, represents the extent of variation between study level relative treatment effects on each contrast. This might be due to differences in treatment effect modifiers or slight differences in design of trials, or for merging different doses. You might have all this sort of heterogeneity mixed in here. The NMA commonly, or standard network meta-analysis, usually assumes the same sigma squared for all contrasts, as the evidence is usually quite sparse. So we need at least 2 studies on the same contrast to be able to estimate what this sigma squared looks like, how big it is, or how small it is. There are 2 problems with just assuming the same sigma squared in our connected RCT and disconnected RCTs and single arm studies. So variation is potentially different. It might be larger, or is almost, I would almost say it's certainly larger in the single arm studies. But also, if we allow the disconnected RCTs and single arm studies to influence the estimation of the sigma squared in the connected RCTs, will again interfere with randomization, because we're using this disconnected data based on imputed μi's to tell us something about variation in the connected network. So we'll bias our results. So we need to assume they're totally different, totally separate. So we do assume these different sigma squareds, but the disconnected network will often be even more sparse than the connected network. So to overcome these identifiability issues, we can use the sigma of the connected network as an informative prior for the sigma dashed of the disconnected network. Or we can use Turner informative priors. But we need to be sure to avoid any sort of backward transmission of information from the disconnected network to the connected network. So our picture for this random treatment effects for both ALM and reference prediction is that we've got some connected network with the sigma squared and some assortment of μi's. So we take the baseline effect μi's, take informative priors based on the sigma squareds to tell us what the sigma squared dashed in the disconnected RCT should be, and what the sigma squared dashed in the single arm study should be. And there's one final technical niggle about doing this in the reference prediction and aggregate level matching, is that we need some sort of correction for multi-arm RCTs. See, trials with more than 2 arms will have more than one relative effect delta, but these are going to be correlated because they're relative to the same baseline arm on treatment B. So under reference prediction for disconnected RCTs and also for ALM, we need to adapt any corrections because the relative treatment effects are now always relative to the reference treatment 1 and not a common baseline arm of the RCT. So when you do actually go through with the steps of adjusting this, we end up with multivariate normal distribution with AI, so for the number of arms, rather than AI minus 1 in the independent baselines random treatment effects model. This is only if you're very into this, you'll see what this difference is. But just note that we have thought about this. And just note again that a disconnected RCT specific heterogeneity variance is being used in this correction. And you can convert this into a univariate distribution for open books. So I'll just pause quickly for questions before I show this test case on atrial fibrillation.
Okay, so Howard, there are a couple of questions that have come through. One is from Goethe Rupta. You talk about the connected portion of the network. What if there are, say, two connectivity components of nearly equal size?
I think I didn't quite hear the question. Sorry, there was interference. And I see something about the questions don't show up fully in my list. But I think you're asking, in my hypothetical scenarios, I've got the networks look very similar in size, the connected bit and the disconnected bit. Obviously, that's not always the case. In our pulmonary arterial hypertension case, we did have 10 treatments that were connected, 1 that was disconnected. And it's often the case that you do have this much smaller disconnected network. And that's useful for reference prediction because you end up having a lot more evidence on the bit that you're trying to model, like the reference treatment. We want lots of trials on that. And also for aggregate level matching, if there's a very large connected network, that gives us a lot of options to choose a good matching and good representation of how one of the connected treatments would have done in the disconnected network. So it's desirable to have a much larger connected network than a disconnected network.
Right.
Was that the question? Sorry.
Yeah, no, I think that addresses it. The second question was, Marifao Piera, this approach does not preserve randomization from the non-connected part of your trials. Is this a problem?
Yes, it is a problem because we're putting this artificial MUI in, so we're interfering with randomization in the disconnected RCTs. It's obviously not a problem for the single-arm studies because there was no randomization to begin with. But yes, this is a disadvantage. And also that the sigma squared, if it isn't identifiable and then we're using some informative prior, that's not giving us a totally unbiased picture. So I accept that as a limitation.
Okay, well, I think we might let you carry on at this point. There are some more questions coming through, but I think we can address those when we get further on.
Yeah, sure.
Right.
So I'll just show, this is a quick constructed example, and then I'll show a more formal simulation study. So this application to atrial fibrillation was really just to check our method was doing what we expect. So we considered the key outcome of preventing ischemic stroke in atrial fibrillation. The reference treatment was fumarin, also called warfarin. Now the network was connected, but we're going to artificially disconnect it. So we know what the true answer is because we have a connected network, and then we just want to see how close we can get to that true answer using our reference prediction and aggregate level matching methods. So the network looks a bit like this, where you've got a lot of treatments in this non-dabigatran subnetwork, and then we've only got one trial comparing 2 different doses of dabigatran that's disconnected. That's for the disconnected RCT scenario. And then if we're assuming that we've only got 2 single-arm studies on dabigatran 110, dabigatran 150, then we've got the same also connected subcomponent. So we first would look at the relative treatment effects in the connected component. So in black, we've got all RCTs, so that's sort of our true answer. Red is the reference prediction, what it's telling us about the connected treatments, and then green is aggregate level matching, telling us what we see in the connected network. So the point estimates and uncertainty intervals absolutely match. So it's very safe to use, and we did see the same thing when we looked at the fixed treatment effect models. Now, in the disconnected bit, we've got the two dabigatran treatments, and we're now trying to predict the log-odds ratio versus coumarin. Both reference prediction and ALM appear to have good coverage because their credible intervals completely cover the black interval, which is the truth found using RCTs. And the point estimates don't appear to be too far from the truth either. Fixed effects analyses gave the same result, but with much tighter credible intervals. If we'd assumed that we only had single-arm studies on dabigatran 150 and 110, this is what we would get if we tried to predict it. So again, the point estimates are close, and coverage is good, but no for ALM, and this is because a study is obviously being matched to it, which has a very low precision baseline, so we end up with this very wide credible interval. So we need to be careful when we're choosing or matching RCT that yes, it does match, but also that there's enough evidence in it to give a reasonable prediction that isn't just noise. So our summary so far, we found that this reference prediction ALM, they have the potential to reproduce treatment effects using single-arm studies, disconnected RCTs. Theoretically, they avoid interference with randomization in the connected RCTs. Reference prediction, we think, might be safer as it's more conservative, and random effects requires some assumptions on the heterogeneity variance. So next, I'm going to show you a little simulation study where we try to assess how ALM and reference prediction would do in other situations. So the basic geometries to explore, we've here got three connected treatments. Now we've got a disconnected RCTs comparing treatments 4 and 5, or assuming that we've got single-arm studies on 4 and 5. Because we're interested in varying just what affects the performance of aggregate level matching and reference prediction, we're only going to vary the number of connected RCTs, but not the number of disconnected RCTs. Because if you've got more connected RCTs, that gives you more evidence to fit your reference prediction model and more choices for the aggregate level matching. So it comes back to the very good question earlier about the relative size of these two networks. And if you did have more treatments, you'd actually do even better because you'd have a greater number of choices. But for here, we're just considering this scenario where we only have 3 treatments, but we're going to vary the number of trials. And in all scenarios, we're going to assume we've got 5 disconnected RCTs comparing 4 and 5, and 10 single-arm studies comparing treatments 4 and 5, or just on treatment 4 and treatment 5. The number of RCTs in the connected component, we've got 3 scenarios. One where there's 2 on 1 versus 2, 2 on 1 versus 3, and 1 on 1 versus 2 versus 3. So in all scenarios, we've got a 3-arm RCT, and then we just gradually increase it. So the largest has 50 trials in total. And we're going to fix the size of the trials at 100 patients on each arm, because our interest is in differences across arms rather than within arms. Although greater numbers of patients might improve the predictions, the reference prediction in ALM, so that's something we might consider later. Our underlying model for the baselines is the same as the underlying model assumed in network meta-analysis and reference prediction, where this mu s for some study is normally distributed around a mean m, has some covariate effect beta, xs is the covariate value. We choose m arbitrarily to be normally distributed around 0.51, so this sort of determines the scale for the other parameters. So when we say that the covariate values themselves are also distributed around 0.501, it means they have roughly the same influence on average of these two as the mean effect. We're going to explore different scenarios on the beta, so the strength of the covariate effect. See the next slide. And this IS equal to disk is an indicator for the trial being disconnected or a single-arm study. And the gamma is the additional variation in baseline response in such studies. This gamma will represent differences in prognostic variables between the RCTs, the connected RCTs, disconnected and single-arm studies. If this gamma, this difference was non-zero, we would imply the random reference prediction and aggregate level matching might be biased. Whereas if it is 0, then it tells us, it would imply that the prognostic factors are very similar between these different components. So we might actually get good performance of the models. So we're going to consider two scenarios: gamma equals 0, we expect good performance, and gamma being normally distributed around 0.5 and 1. So again, on the same scale as this mean effect. The scenarios on the prognostic variable, this XS has an effect beta. This beta represents the strength of the prognostic variable. A stronger relation would imply a better performance of reference prediction than ALM, and a weaker relation will obviously imply worse performance. But we're only going to consider one prognostic variable, XS, and this is without loss of generality, because if there's unaccounted extras, that will be captured in either the M or the gamma, or if you had accounted extras, so extra variables in our model, it would just imply a stronger beta. So we make this assumption again without loss of generality. And we assume this beta can either be weak or strong. So it's either 5 times weaker or twice as strong as the mean effect. And we assume that this beta, or this XS, is not an effect modifier, because effect modifiers are a problem for both connected and disconnected networks. So it's not of interest to our analysis, because it's not a problem we're purporting to solve. Power calculations, and we followed Morris 2019. The coverage is just the 95% credible interval. If it includes the truth, it's a success. If it doesn't, it's a fail. Then we report the proportion of successes. That gives us the coverage probability. We also report the bias. And then we can work out for 100 simulations, we've got a mean squared error for the bias of 0.015. That's on the log odds ratio scale. So compared to a treatment effect with mean 0.5, that's reasonably good. And hence in 100, it gives a coverage of about 0.0, and a mean squared error of coverage of about 0.047, and we'll see that that's actually sufficient. But we will likely increase this to NSIM 1000 as a final confirmatory simulation. So the total number of scenarios we've ended up with is we want to look at both fixed and random effects. I'll only present random effects, but fixed effects were similar, just worse. We're going to look at disconnected and single arm studies. We'll look at the beta, the prognostic covariate being strong, gamma, the difference between the connected and disconnected networks being 0 or strong, and then various different sizes of the connected RCT. And this gave us 24 scenarios in total for the fixed and random effects. It's very easy for scenarios to multiply when running these simulation studies, so we're trying to keep it as focused as possible. So these are the results for random effects, where we've got 100 simulations. So we've here got one row each for each of the different methods and scenarios. So the RCT only, that means what we would get if we were just using the randomized control trials. Then ALM single, that's aggregate level matching on single arm studies. ALM disconnected is ALM on the disconnected RCTs. RP is reference prediction on the single arm study. RP disconnected is reference prediction on the disconnected RCTs. And this is the bias on the connected network. So we were expecting this to be very similar, and it is. So note that just using RCTs only on the connected network, that's the same as a standard NMA. So this is the bias that you get estimating these treatment effects using standard network meta-analysis. It's about 0.02, and we see that it's very similar across these different methods. These results are on the log odds ratio scale. The true mean is 0.5, so a bias of 0.02 is less than 10%, that's like 5% or something. Also, the bias may be 0 because the mean squared error is 0.015. But basically, the bias between the connected and disconnected bits of the network agrees. So this is again telling us that ALM and reference prediction are safe to use in terms of not messing up our estimates in the connected network. Then we can look at the bias in the disconnected portion of the network. So here is the scenarios where the gamma is 0, so the prognostic factors are the same between the connected and disconnected networks. So this is a good scenario to be doing ALM and reference prediction. And we see where the beta is weak or strong. We would like to see some sort of improvement in the method as we go from weak to strong, because for strong scenario, we'd expect a better performance of ALM or reference prediction. We see it doesn't make a huge difference between the two. And that we can just look at this in summary, that the bias appears to be larger in this disconnected network than in the connected component. That's expected, but the bias is still only around 10 to 22% of the mean log odds ratio of 0.5. So we're not really too far from the truth. But we can't consistently say that ALM or RP are better, and we also can't say that stronger covariate gives lower bias. So this would be implying that it doesn't matter which variable you choose for the covariate because you're still not really improving your predictions. You can then look at coverage in the connected components. So this is in the bit where we have RCT. We're seeing that very similar results across the different methods. So again, it's safe. It's 99% or 96% or worse. But then the coverage in the disconnected network. So ALM on single arm studies is between 50% and 75%. So that's not very good. ALM in disconnected is between 70 and 86%. So that's a little bit better. And then reference prediction appears to be between 80 and 95% for either single arm studies or disconnected networks. So again, it's capturing the truth more reliably. And we saw earlier that the bias in the disconnected was relatively similar between the reference prediction and aggregate level matching. So it appears that reference prediction is giving good coverage and reasonable bias. Now, ALM has worse coverage, in particular for the single arm studies, but note that this is twice the coverage that we saw when we looked at fixed effects models. So this is all for the case where the gamma was 0, so where the prognostic factors were similar and we could trust that we could do good predictions. But if the gamma was strong, the bias increases. So this is sort of a worst case scenario. The bias is now around 50% of the true log odds ratios. So reference prediction and aggregate level matching are off by 50%. And this is because the noise in the prognostic factors can't actually be modeled by ALM or reference prediction because it doesn't have any information on it. The coverage also drops. So aggregate level matching is now between 40 and 70% in the single arm studies and 65 and 85 and then disconnected. Reference prediction has dropped to between 70 and 85%. So reference prediction is still not doing terribly. It's say 80% coverage and bias of about 50%, but obviously it's doing worse if the prognostic factors are not the same. So if you've got some disconnected RCTs that are in a slightly different population, it's less safe to do reference prediction or aggregate level matching, which is intuitively true. So the summary of this simulation study is the bias obviously depends on whether the baseline response is similar in the connected and disconnected components. It ranges from 10%, which is reasonably good, to 50%, which is quite bad. Although even the 50% does give some indication of the order of the treatment effect. It'll tell you if it's much, much bigger or much, much lower. But we can't model this, unfortunately, except maybe if we imputed clinical opinion. Reference prediction appeared to have good coverage in all cases, but that's because predictions are just so uncertain. ALM had poorer coverage in all cases, and we can't say if stronger covariates really improve the prediction. I'm not sure if extra simulations are going to resolve this because the MSE is already quite small compared to bias. So I'll just close with some remarks about these methods. So we found the reference prediction in ALM can reproduce the treatment effects if the conditions are good. ALM has poorer coverage, but the bias can be low, and reference prediction is better coverage and similar bias. We see that both of them avoid interference with randomization in the connected RCTs, but as someone pointed out, you're right that it does still interfere in the disconnected component. We would strongly recommend, if you're doing this, cross-validation to assess reference prediction or ALM. So similar to how we looked at the atrial fibrillation network and artificially disconnected it, you would do the same with your connected component and see if you can reproduce the treatment effects. But reference prediction with random treatment effects might be the safest option because it's the most conservative. So next step for us, we might update the simulation study, increase trial sizes, more simulations. We could use external information, so to inform reference prediction models, so say a cohort study or observational evidence. And we might want to extend this to individual patient data. But we need to remember here that ALM and reference prediction are really methods of last resort for decision makers. We're not saying that you should go ahead and do this in a scenario. High quality RCTs or at least access to individual patient data are still very much needed. And this is what I presented here is more a backup. And one other closing remark, which I haven't put here, sorry, is that you could, if you're interested in doing expected value of partial perfect information or expected value of sample information, using these methods might give you some representation of the uncertainty on the disconnected networks and thus the value of running a new trial. So that's one alternative application. Sorry if I've gone over. There are some references, acknowledgements. The DOAX was funded and NIH are currently fund me. Thank you very much for your patience.